So welcome everybody. This is seventh DGD session and it'll be on oscillatory motions. So this will be covering chapter 15 of your book completely. So I have like picked around 7 questions for today. I hope you find them interesting enough. And if you have any doubt, you can type in the chat or you can ask me during the session as well. I've given you microphone, right? So let's do it. Let's start. Just a sec. I'm just reorienting stuff. So might take a little. Yeah. So you guys can see my screen, right? Like without any problem. Yes. Okay. Let's dive on to the first question. So this DGD is all about today's DGD oscillatory motion. Okay. And that's chapter 15th of your book. So the first question, I'll read the question. It's a 0.6 kilograms block attached to a spring with force constant 130 Newton per meter is free to move on a frictionless horizontal surface. So given is a mass attached to a spring on a frictionless surface. So this is your frictionless surface. That means you have to worry only about the Hooke's law. The block is released from the rest. In the diagram you can see this is the rest position and it's been displaced by 0.13 meters. This is the easiest question. So it asks you about it asks you about the force on the block. If you remember Hooke's law, where x is your displacement. Okay, let's say this is the origin. Then we say on our right of the origin, distance is positive. That means force is simply minus 130 Newton per meter into 0.13. Okay, B part. It's acceleration. So acceleration at that moment is given by force as ma. At that instant, you have force. Put the value there. Then you can find acceleration as force by m, and m is given as, or I'll write it. It's good. I think it's straightforward. So I can safely move on to the next question. If you guys agree, just say yes. Oh, thank you. Thank you, Anthony. So let's move on to the next question. The first one was just to give you the hang of that. I know. Okay. The second question is, a 7 kilograms object is hung from the bottom end of the vertical scrim fastened to an overhead beam. So as you can see in the diagram, there is a beam. Let's This is the beam from which a spring is hung, and the object is set into vertical motion. We have been giving time period of 2.60 seconds. Okay, it says, and mass is also given. Let me write that as well. Find the force constant. Let's see the formulas. You know, A part is only no A part. Let's say answer. Omega is given as root K by M, where K is your spring constant. Okay, and omega is given as 2 pi F or 2 pi by T, or T is given as 2 pi by omega, or 2 pi root K by M, or 2 pi root M by K T. Therefore, we have to find spring constant. Now I can find directly from this equation. T square can be written as 2 pi square M by K. K can be written as 2 pi square M by T square. Mass is given, T is given, so it's just you have to apply that, substitute the values, and you'll get the answer. Is it good? Okay, so I can move on to the next question. Okay, so as you can see, the next question says, a ball dropped from the height of 4 meters makes an elastic collision with the ground. Assume no decrease in mechanical energy due to air resistance. Show that the ensuing motion is periodic. Okay, so and determine the period of the motion and force. Okay, let's see. That's 3 parts. Let's see. Okay, so let me highlight the main point. The collision is elastic. What does that mean? Elastic collisions means means that your momentum is conserved, right? It's resistanceless, okay? There's no force of friction. So if my ball hits a ground without any resistance and it's elastic, that collision elastic nature, then it will come back to the same point, right? And it'll keep doing that. So that is enough to say that this motion is periodic. Did you get it? I can explain the other way as well. Okay, thank you. Thank you, Billy. B part, determine the period of the motion. Newton's second law tells us x is ut plus half gt square, right? If it starts from rest, that means u is 0. That means x is half gt square, right? So t is 2x by g to root. You have x, you have g, you can find the period. Root 2 into 4, 9.8. Okay. Okay, so this is the question for you guys. Is the motion simple harmonic? Who will tell me the answer? Okay, just type whatever. Just type the hunch if you guys. Doesn't matter whether it's correct or wrong. So Billy says yes, it is. Anybody's not in favor? Or everybody's in favor? Just guess. Or you don't need to guess. You're really not sure? Okay. That's fine enough. I wouldn't be able to explain it. Yeah, I'm not asking for explanation. I'm just asking for hunch. Your guys, like, what do you guys feel? You feel a ball that is dropped and there is a less elastic collision. Would that be a simple harmonic? Just, I'll give you a hint. Just if you remember how you derived the simple harmonic equation, it's from the Hooke's law. Does it satisfy Hooke's law? If it satisfies Hooke's law, then it's good enough. But would it be able to satisfy this type of situation? Okay, so I assume everybody is saying yes. It's okay. It's okay. It's okay. I'll give you the text as well. Thank you. Thank you for trying. And Hooke's law. Hooke's tells us forces minus kx. That means m d2x by dt square is minus kx. That means your acceleration is in opposite direction to your displacement. Okay, that is directly proportional but is in opposite direction. But here only force you have because of elastic motion, it is mg, right? That is m d2x by dt square minus mg, and this is a constant, this is a variable, So that means this motion is not simple harmonic. So not simple harmonic. Does that make sense? Okay, so if you guys understood, I can move on to the next question. So the answer is it is not simple harmonic. Simple harmonic, you just need to satisfy this condition. So let's ask. So if the I'll ask you another variant of this question. If the collision was inelastic, would it be simple harmonic? Beatrice is typing. No, I don't know. Yeah. So no is the right answer. You knew. So so and I'll tell you the answer. Why? Because even if there is another term for friction here, that is your resistance from the ground, this would still not satisfy your Hooke's law equation or damped harmonic oscillator equation. So it won't be able to. This is damped harmonic oscillator, right? I'm not going to that right now. So I hope it makes sense. Um, if you all agree, then I'll move on to the next question. Billy's typing. I'm waiting for the comment. It's okay. It's okay. You can still ask me the question if you have any doubt about anything. If you don't understand anything and you want to ask something that your prof covered, you were not sure or you didn't ask him, you can ask me. Yeah. Okay. So let's move on to the next question. A simple harmonic oscillator of amplitude A has total energy E. Determine the kinetic energy and potential energy when the position is 1/3 the amplitude. Let's see what's given. A, B. Total energy of the simple harmonic oscillator is given as so total energy is the sum of potential energy plus kinetic energy. So what is potential energy? Half kx square. What is kinetic energy? Half mp square. Okay. Now the first part asks what is the kinetic energy if the position is 1/3 the amplitude. Okay. So Ke is half Ka square minus half kx square. Okay, I want to clear here. Total energy is half Ka square. Okay, you guys remember this formula, right? I can derive it for you if you want. It's just total energy is the sum of potential and kinetic, and then of simple pendulum is half K square. So as simple as that. Now put it as 1/3. So given x is a by 3 half k square minus a square by 9. So ke at x equals to a by 3 is half k a square by 9, that is total energy into 8 by 9 total energy. Do you guys agree with me? If you agree, then I'll move on to the next part. I just substituted for x as amplitude by 3 as given in the question. Okay, let's go to the next part of the question. It says, what is the PE, potential energy? Potential energy is given as half k a square minus half mv square, right? At x equals to a by 3, PE is given as half k a square minus 8 by 9 half k a square, which I can write as 1 by 9 total energy, that is half k square. You guys agree with me? So at x a by 3, your kinetic energy we calculated in first part was 8 by 9. I just substituted that here and we get the answer for potential energy, that is 1 by 9 of total E. It's okay. I'll move on to the part C. For what values of position does the kinetic energy equals 1/2 the potential energy? So just a sec. So the question was, at what values of position does the kinetic energy? Okay, so we have to find the values of position for the kinetic energy 1/2 the potential energy. Okay, so total energy Ke plus Pe, that is using the condition given, that is half of kx square plus kx square half kx square 3 by 2 half kx square. So half Ka square is equals to 3 by 2 half kx square. You cancel out these terms and you'll find that is it okay? I just substituted kinetic energy as half of potential energy as given in the question. Yeah, thank you. So there's again question for you guys. Are there any values of the position where kinetic energy is greater than the maximum potential energy? So thing to focus upon is maximum potential energy. So who all of you who are in favor, just say yes, and others can say no. So are there any value of position possible where the kinetic energy is greater than the maximum potential energy? Bit to say no. Anybody says yes? Yeah, that won't be possible. So that was a trick question. Yes, it's not possible because if TE max, TE can be either equals to KE max or PE max. So the minimum value for any of them can be zero. So that's why the kinetic energy can never be greater than the maximum potential energy. The word maximum. Okay, that would violate the conservation of energy. That is the most sacred law of physics. The conservation of mass and energy, the conservation of mass energy is the most sacred laws of physics, among the most sacred laws of physics. So mass, momentum and energy should be always conserved together. It's called conservation of momentum energy. Okay, let's go on to the next question. Okay, we've been given a pendulum of mass 0.25 kilograms, given mass 0.25 kilograms, and the length of a string is 1 meter, and this is executing a simple harmonic motion. It is displaced through an angle of 15 degrees. Using the analysis model of simple harmonic motion, that is SHM, find the maximum speed of the bob. Okay, I'll start from the basics for that. If this is your simple harmonic motion, if you guys remember, displacement of a simple harmonic motion is given by this, then dx by dt, that is velocity, is given as a omega sine omega t plus phi, and acceleration is given as so the question asks for maximum V max, that is a omega. We have omega. Yeah, so let's find it. We don't have any of them, so let's find it. It's not given directly in the question, so omega is given as root g by L, right? That'll be 9.8 divided by 1. And what is A? I wrote as S before. I can write as A. This is A. A is radius into theta. This is your theta. Then that is 1 meter into 15 into pi by 180 for radian. This is just radians conversion. Converting the angle 15 degrees to the radians, that is pi by 180, and then you get A, substitute back, you'll find R max, V max. the B part, A max is maximum angular acceleration is, as you can see, I derived here, A omega square. You calculated A, you have omega, substituted here, you will get A max. The maximum restoring force on the bob. So C force is force max is given as M A max. That's your answer. A max you calculated in the part B. Any questions on this? If not, I'll move on to the next part. That is question number 6 for today. Okay. That's a little proof question. I think it might be useful for the exam. Your prof might ask you. That's okay. People must be having some really useful thing instead of studying or something. That's why they're not here. So moving on to the next question, that is sixth question. I thought that's why I picked up this question. I thought this will be useful in your exams. Your prof might ask you to prove this. Some profs likes proofs. I don't know about yours, but yes. Show that the time rate of change of mechanical energy for damped undriven oscillator is given by dE to prove. That's okay. That's okay. Then consider this as your practice. Yeah, final might be good for the final. Yeah, or consider this as a practice. Okay. I pick questions. If I would be prof, I would pick the same questions. So I just choose like that. So to prove dE by dt is minus bv square. Okay. And hence is always negative. So we have to prove that for a damped undriven oscillator, that rate of change of energy is always negative. I think it's not very hard to imagine. Physically, we can think about it. There is a harmonic oscillator, let's say like this, and it's damped mean it's on a surface with a resistance. So there is a resistance on the surface. So let's say it's a scratched surface, not even, it's not polished surface. So there is a resistance. That means it's a damped oscillator. So physically we are trying to think about it, that rate of change of energy is negative. That means if it's executing a SHM, then it will be damped. That means your internal energy will be decreasing, or total energy of the system will be decreasing with time. Does that make sense? Okay, so that will be decreasing with time. Okay, so they're just asking us to prove it. So to do so, differentiate the expression for mechanical energy. Okay, let's prove it. The proofs are the easiest and the fun to do. So let's differentiate it with respect to time, dE by dt, or you can write it as E dot. This is also a notation. Differentiation with respect to time can be written as a dot, and if it's double, then you can write two dots, but it's single. So, okay, can be written as half m 2v, yeah, dv by dt plus half 2k x dx by dt, right? Or I can make it, instead of differentiating with respect to, I differentiate with respect to x. I'm not taking b as a variable. I can make it easier. I can write it dx by dt. That means d2x by dt square. Does that make sense? And there won't be 2. 2 will cancel out. I just made a mess there. Sorry. I'll redo it. I was just trying to simplify it. So it's direct differentiation. I'm writing, because I'm considering with respect to x everything, so that because there was x variable here as well, so that will make it easier. This, you are doing another differentiation with respect to that will change out to be, now does that make sense? I think so, but that time I made a mess. Right? And your equation for damped oscillator is md2x by dt square minus kx minus bv, right? So, and sorry, I'm missing a v here. I'm very sorry there. md2x by dt square, and I'm substituting back in this equation. I'll get E dot as mv minus kx minus bv, okay, and plus kxv, right? There shouldn't be m, so E dot minus kxv plus kxv minus bv square E dot or de by dt minus bv square. Okay, any problem here? So what I did here, I made the confusion. Sorry for the confusion here. I was just trying to simplify it so that you guys would get it easier. That's what I was writing before. I'll just to clarify so that. Is it clear? So if any confusion, you guys can ask. Otherwise, that's the proof. So I'll just tell you the notations. If you write this, like this, this can also be written as double dot. This is just a notification, no notations in physics. A differentiation or time derivative is can be represented by dot. Yeah, it's just moving things around. Yes, I'm substituting from the damped harmonic oscillation equation back to the total energy equation in terms of little differentiation. All I did was take a derivative with respect to time. That's all I did. I just took derivative with respect to time. So nothing more than that. Simple proof. Okay. So moving on to the last question. So this is the seventh question. I think that's the last one. So an object of mass m moves in a simple harmonic oscillation with amplitude 12 on a light spring. Its maximum acceleration is given. Regard m as a variable. So m mass is given as a variable. Okay, we can just take it as m in kilograms. Find the period of the object. Let's do it. A part time period is given by 2 pi by what the just a sec, that was into shapes. So 2 pi by omega. Okay, and what is maximum acceleration? A amplitude into omega square. I derived it in question number 5th, that is here. So acceleration max is a omega square, right? So a max, a omega square. From here you can find omega square as a max by amplitude, or I'll just root it. Okay, and acceleration is given as 108 with an amplitude of 12.0 into 10 to the power minus 2, because it was in centimeters. Okay, sorry, so we don't need that because acceleration is also given in centimeters. So centimeters. Okay, so omega, we have omega, we can use that to find total time period. That's your part A. Part B is frequency. Its frequency is 2 pi. So I'll write it like that. Omega, you write it as 2 pi f, right? Therefore, f is omega by 2 pi, or you can find f directly by 1 by t. Okay, find the maximum speed of the object. See, maximum speed V max is S omega. So S, or amplitude, I denoted by A, so I'll continue with that notation. So A is given as 108 centimeter, 12 centimeter is the amplitude, and omega we calculated in B part. Okay. Fourth part, find the total energy of the object spring system. So seems like total energy is difficult to find, but it's not. Ke plus Pe, right? We don't have K, like spring constant. It's not given, right? But we have mass given as M, kilograms. I'll write it as mass, but we don't have K. How do we find now total energy? You know, total energy can also be written as Ke max or Pe max. And in the previous question, we had V max, we used that to calculate Ke max. That can be given as half mv max square. From here, we substitute from the previous, then we can find the max total energy. Do you guys agree with that? If it makes sense, I'll move on to the last part. Okay, thank you, Billy. Find the force constant of the spring, finally. Let's find the force constant. E omega square is given as K by M. Then omega can be, or M omega square is K. You have M, you have omega square. You can substitute the value to find K. That's your spring constant. So I hope you got this question as well. So that was the end of questions for today, and I'll conclude the session. We covered forced harmonic oscillator, simple harmonic oscillation, oscillatory motion, periodic motion, and more or less your chapter 15th. I hope you guys got it. If you guys have any question, we have time, we can discuss. Or any conceptual question, yes, we can discuss. And okay, thank you very much, Billy. And I again apologize. I've been unable to send you a PDF before because I've been logged out of my account because of some multi-factor authorization problem with my account from the university, and because they are not operating at full capacity, service desk or IT help desk is unable to help me. And so they wanted some couple of weeks. That's why I couldn't send you those PDFs. Also, I'll ask the prof to upload the PDF. And for the YouTube, you can go and check on YouTube anytime. I uploaded the videos there. Would we be able to do question 37 from chapter 15? I have to open WebAssign for that. But if you have problem, I can solve it for you. That's what you want? Okay, just give me a sec. Oh, this is the old book I have. Let me see which question in this old book. Can you send me the... Oh, I don't have the ID. I cannot log into the ID. Oh, shit. So it's forced oscillation. Which section is it? It's damped oscillation, forced oscillation, pendulum. If you can tell me, I can look into it. Review a particle of mass. Okay, let me see. Where is this review? Review. Let me check. Let me find it. Okay. So the two objects stick together. What is the new amplitude of vibration? I'm just reading the question. So just maybe wait a couple of minutes. Okay. It's better if I can find it here. And you know what? I'll open my account of... Hey, please, you feel free to leave. I'm just solving it for Beatrice, I guess. Oh, if you don't mind, I'll open my account. That is WebAssign. Yeah, I'm opening that. You can see my screen, yes? Yeah. So I think I'm near your question. So it's in the additional question, right? So is this one? Okay, let me read the question. Or I can do better. Okay, later. I can just read the question here. Is it okay if I just tell you how to do it, or should I solve it for you? I can solve it, but it's just I need to copy paste this question there and then solve it on there. Otherwise, I have to go back and forth between the questions. Okay. Okay. So for the first part, what is the new amplitude of the vibrating system after the collision? Let's go on to the question first. I'll break it down. If you don't get it, you can still send me an email. My email is still logged in my cell phone. I can check your email, and you having some problem, I can send you the solution. Okay. I mean, I will solve it and send you the solution, kind of like that. And I'll tell you the steps here, if that's okay. Sounds good? Okay. Okay. So a particle of mass 4 kilograms is attached to a spring with force constant 100. That means K is given, M is given, you can find omega, right? Right. This is the how I solve it. Like whatever is given, so I just try to see what I can do with the given information. It is oscillating on a frictionless horizontal surface with an amplitude of 2 meters. We have given A amplitude. A 6 kilogram object is dropped vertically on top of the fork as it passes through its equilibrium point. The two objects stick together. What is the new amplitude of the vibrating system? So, so as it sticks together, that means the collision that happens is inelastic. I'm just finding this from what is given in the question, right? And there is, and you have to find now the new amplitude of the vibrating system, right? That means you apply the momentum conservation. I mean, so before and after, to find that, you need to find the maximum velocity that is given as omega A, right? So the momentum before and momentum after. So for before, your object, 6 kilogram object, it sticks. That means it has zero velocity, and your 4 kilogram object is there as well, right? And that has Vmax, you already calculated, right? I can write that equation for you. Maybe it's a little confusing. I mean, I can see it there. So I'll write that equation. My pen draw.